Alright, in this video we're going to be taking a look at the combined gas law and Dalton's law of partial pressures along with our water partial pressure. Alright, so our combined gas law is going to be our P1V1 divided by N1T1 is equal to our P2V2 divided by N2T2. Our N will be our number of moles, the P will be for pressure, the V will be for volume, and T will be for temperature. So how we're going to solve these different problems is that we are going to cross multiply. We're going to solve for the unknown by dividing the opposite side by the known variables. Now, if the variable does not change, we will not put it in the equation. And if the variable is not addressed in the problem, we do not put it in the equation either. So we are going to only input the variables that we need and solve for the unknown. So taking a look at our first example, let's say if I initially have a gas at a pressure of 12 atmospheres, a volume of 23 liters, and a temperature of 200 Kelvin. I then raise the pressure to 14 atmospheres and increase the temperature to 300 Kelvin. What is the new volume of the gas? So the first thing that I always like to do is that we're going to go ahead and label our different variables that we have. So our initial pressure, denoted by our P1, will be our 12 atmospheres. The next variable and everything that I notice is going to be my initial volume. So the volume that I start with will be 23 liters. And then the initial temperature that I'm starting with is 200 Kelvin. Now the problem also gives us, we have the final pressure, so our P2 will be our 14 atmospheres. The final volume is what I'm looking for, so that is going to be the unknown that I'm solving for. And then our final temperature, our T2, is at 300 Kelvin. So right here I have listed out all of my variables that I need. I know that I'm solving for my V2. I should notice that my number of moles is missing, so I get to ignore it. So taking a look at our equation. So I have my initial pressure, that will be multiplied by my initial volume, divided by my initial temperature. I'll set this equal to our final pressure times our unknown variable. So we're trying to solve for the final volume, and then dividing it by our final temperature of 300 Kelvin. Now I will do this by cross multiplying and dividing. So I'm going to take all of this, multiply it together. I'm going to take all of these and multiply them together. And so what I will end up with will be our 82,800. I will set that equal to my other side being multiplied together. So 2,800 multiplied by my unknown variable. I will go ahead and divide both sides. And then whenever I solve this, I should get 30 liters as my unknown variable or my final volume. Now, we should notice in everything that our final is in liters because our initial volume is also in liters. Let's go ahead and take a look at another example. Alright, in this one, a gas has a volume of 28 liters, a temperature of 45 degrees Celsius, and an unknown pressure, has its volume increased to 34 liters and its temperature decreased to 35 degrees Celsius. If I measure the pressure after the change to be 2 atmospheres, what was the original pressure? Alright, so in this one we are asked to find what is the original pressure. So we know that our P1 is going to be our unknown variable. So our P1 is going to be the unknown, what we're solving for. Our initial volume if we go ahead and read the question, we should notice that it is 28 liters. Our initial temperature, so our T1, will be 318 Kelvin. Our final pressure will be our 2 atmospheres. Our final volume will be 34 liters. And our final temperature will be 308 Kelvin. Now, we get to plug all these variables into our equation. So our P1 is the unknown multiplied by our 28 liters divided by our 318 Kelvin. Set that equal. Final pressure of 2 multiplied by the final volume of 34, all divided by the final temperature of 308. We are going to go ahead, we are going to cross multiply. So we're going to multiply all of these together, and then we're going to multiply all of this, divide and solve with our normal algebra that we would do, and we should get that the initial pressure is 2.5 atmospheres. So again, how we get that is that we are going to cross multiply and divide, solving for that unknown variable of P1, or the initial pressure. Alright, let's go ahead and take a look at our next example. So let's say if I have 21 liters of gas held at a pressure of 750 kPa and a temperature of 900.0 Kelvin, what will the volume of the gas be of the gas if I decrease the pressure and temperature to STP? So this and everything is going to be when the STP comes back in. So it is going to be the standards that we have. So it is going to be our 273 Kelvin and our 1 atmosphere of pressure. Or, in this case, we need to look at our kPa, so the kilopascals, in order to find the standard. So we should look back at our notes. It'll be our 101.3 kPa and our 273 Kelvin. So these are going to be our standard pressure and our standard temperature. We're able to go ahead, we can plug in all of our different variables that we have. So we are going to get our 750 kilopascals multiplied by our initial volume of 21, all divided by our initial temperature of 900. Set this equal to, so our STP, so the standard pressure will be our 101.3. The unknown variable that we are solving for is our V2, all divided by the standard temperature of 273. Same idea as before. We are going to go ahead, we are going to cross multiply and divide. So cross multiply all of this, divide to find the V2, and we should get that our final volume will be our 47 liters at the end. Taking a look at our next example. So bringing in the idea of a hot air balloon. So let's say in everything that we have a hot air balloon, it has its volume of 1.00 times 10 to the 5th liters when at 25 degrees Celsius. Okay, what will be the new volume if the air is heated up to 65 degrees Celsius? All right, now, making sure we need to go ahead and convert our Celsius over to our Kelvin. All right, so our Celsius to our Kelvin, our 25 degrees Celsius right up here. If I convert this by adding in the 273, I will get a temperature of 298 Kelvin. If I take a look at our 65 degrees Celsius, go ahead and convert this over. This will give us 338 Kelvin. Now, this one is pretty straightforward. We are only dealing with our volume and our temperature, so we get to ignore all of the other variables. Putting this in, so our initial volume is going to be that 1.00 times 10 to the 5th liters. We are going to divide that by our Kelvin, the initial temperature in Kelvin, so the 298, and we're going to set it equal to, it is asking us to find the new volume, so that is our V2, divided by the final temperature of 338. Now, make sure and everything along with this, just because that 1.00 times 10 to the 5th is in scientific notation, we get to solve this just like anything else. Again, that 1.00 times 10 to the 5th, all this is, in our standard notation, is 100,000. So in this hot air balloon, there is 100,000 liters of air. That's all and everything that the 1.00 times 10 to the 5th is telling us. We are going to go ahead, cross multiply, and divide. So we should end up with 113,000 liters, or if we keep it in our scientific notation, 1.13 times 10 to the 5th liters will be equal to our unknown volume of V2. So this right here is going to be our final answer. Let's go ahead and take a look at one more example. Alright, so let's say everything out on hot days. We have noticed that potato chip bags seem to inflate even though they have not been opened. So very common if you leave some chips in a car on a hot day, you'll notice everything that when you come back, the bag is a little bit more tight. If you have a 250 ml bag at a temperature of 19 degrees Celsius, and I leave it in the car, which has a temperature of 60 degrees Celsius, what will the new volume of the bag be? Alright, so going ahead and making sure we are looking at those degrees Celsius, knowing that we need to convert them. So this 19 degrees Celsius, going ahead and adding in that 273 will get us 292 Kelvin. Taking a look at the 60 degrees Celsius, if I go ahead and add in the 273 for it, I should get 333 Kelvin. So converting those Celsius immediately over to Kelvin. Now, the initial volume of the bag is 250 milliliters. So we'll start with our 250 milliliters on top, divided by the initial volume of 292. Set that equal to, it is asking us to find the final volume, the final temperature being 333. Go ahead, we are going to cross multiply and divide, so we should get 285 milliliters as the final volume. Now, the reason that it is our milliliters is because the initial volume was also in milliliters. So that right there, just making sure that your units remain constant. Alright, let's go ahead. We're going to talk about Dalton's law of partial pressures, and then our water displacement. So, Dalton's law of partial pressures, all it states is that the total pressure of a system is equal to the sum of the partial pressures of each gas in that system. So our total pressure is going to be equal to all of those other partial pressures. Let's go ahead and take a look. So let's say we have a metal tank. It contains three gases: oxygen, helium, and nitrogen. If the partial pressures of the three gases in the tank are 35 atmospheres of oxygen, 5 atmospheres of nitrogen, and 25 atmospheres of helium, what is the total pressure inside of the tank? Now, Dalton's law of partial pressures is extremely nice, is that all we have to do is add up all of these different partial pressures. So we get the 35 atmospheres of oxygen added to the 5 atmospheres of nitrogen, added to the 25 atmospheres of helium. So all we do is add those up, and we should get a total of 65 atmospheres as the answer. And that is going to be the idea behind Dalton's law of partial pressures. Let's go ahead and take a look at our next example. So let's say if the total air pressure in a blast furnace is 100.3 kilopascals, the partial pressure of carbon dioxide is 5.07 kilopascals, and the partial pressure of hydrogen sulfide is 2.03 kilopascals. What is the partial pressure of the remaining breathable air? Alright, so this is asking us to find what is the partial pressure. So not the total pressure, but a partial of it. So we know that the total is 100.3 kilopascals. So all of the total, or all of the partial pressures are going to add up to this total. Now the carbon dioxide is 5.07. The hydrogen sulfide is 2.03. And that just really remains the partial pressure of the air. So we're going to be solving for the pressure of the air from it. So all we're going to do is just solve for that P air through subtraction. So we'll get our 100.3 minus 5.07 minus 2.03. And that will get us 93.2 kilopascals as the partial pressure of our air. Alright, now let's go ahead and take a look at our next example, which is a little bit more involved. Alright, so taking a look at this example, we are going to go ahead and take a look. So let's say that I have a mixture of helium and xenon that is 35.5% helium. The total pressure inside the tank is going to be 15.5 atmospheres. We need to go ahead and calculate the partial pressure of each gas inside of the tank. Alright, now, the idea behind this is looking at our total percentage of our air. So inside of this tank, it is 100% helium and xenon. 35.5% of that is going to be the helium. So we're going to go ahead, 100 minus 35.5, this will get us 64.5% being our xenon. So 64.5% of this mixture is going to be xenon. Now from here, I can look at the 15.5 atmospheres. We can multiply it by the percentage. So I'm going to start with helium. So multiplying by percentage, we are going to go ahead and move that decimal over. So we're going to get our 0.355. So 15.5 times 0.355 will get us a pressure of 5.50 atmospheres of our helium. So this is one part of the question. So this and everything answers the helium part. Now from here, you could also just go ahead and subtract that from the total in order to get the partial of the xenon, or because we already found the percentage of the xenon, do the 15.5 times our 0.645. Going ahead and taking a look at this, we are going to get 9.99, which we are going to go ahead and we are going to round this to our 0.0 atmospheres of our xenon. So those two right there are going to be our answers. All right, let's go ahead and take a look at water displacement. So, gases most of the time are going to be collected over water. Now, because of this, the total pressure measured is going to come from the pressure of the gas and the pressure of the water vapor at that temperature. So a lot of gases are going to be dissolved in water, and so in order to get those gases out, we are going to go ahead, we're going to heat up that solution of the gas and water in order to produce the gas that we need. So changing up Dalton's law of partial pressures a little bit, we are going to get the total pressure is equal to the pressure of the gas plus the water vapor. Now, taking a look at our water vapor pressure table. So all of these are going to be our standards for the water vapor in degrees Celsius. Now, what we should notice is that all of the pressure is in millimeters of mercury. So we need to make sure that any question that we have with water displacement, we are looking at the pressure in terms of millimeters of mercury. Let's go ahead and take a look at our first example. So, when hydrogen gas is collected over water at 20 degrees Celsius, the total pressure measured was 756 millimeters of mercury. What was the pressure of hydrogen? All right, so we have the total pressure of 756 millimeters of mercury. Now, this is very handy. What we're going to do is that we're going to look at this table. So at 20 degrees Celsius, we need to figure out what is the pressure of the water. So if I take a look, we're going to find our 20 degrees Celsius. It provides us with a pressure of 17.5. So our total will be equal to our 17.5 plus the unknown. So the unknown is going to be the pressure of the hydrogen gas. All we do, solve for the unknown. So 756 minus 17.5. So the pressure of the hydrogen gas will equal 738.5 millimeters of mercury. All right, let's go ahead and take a look at one more example of our water displacement. This time, all right, so taking a look at this question, when oxygen gas was collected over water, the total barometric pressure at the time the gas was collected was 760 millimeters of mercury, and the water was at 40 degrees Celsius. What was the partial pressure of the oxygen gas that was collected? All right, so going ahead and taking a look at this, our total pressure at the time was 760. We are at now 40 degrees Celsius. So finding 40 degrees Celsius on our table will be right down here. We should notice that it is at 55.3 millimeters of mercury. So all we have to do is find that partial pressure of the remaining oxygen. So 760 minus 55.3. So the partial pressure of the oxygen will equal 704.7 millimeters of mercury. And that will be our final answer.